Okay, hi everyone. So this is a video for me trying to explain principle of conservation of angular momentum using various real-life situations. So what I heard from some of my students is that many of you cannot really imagine the situation really well. So probably through these two situations you are able to get a better idea maybe. So let's give it a try. First situation. Okay, so this situation involved a toy which you might have seen in quite often in like pasar, let's say. It's called a Hoberman sphere. And yeah, once I play the video, you probably say, oh, this is the toy that I've played before when I was a child. Okay, so let's look at the video first. Oops.
Expanded high moment of inertia configuration, and then we contract it, its angular speed should increase.
Oh.
And sure.
Interesting, right? Okay. So yes, the principle applied here is just principle of conservation momentum, but angular momentum. But how do you actually apply it? Okay. So for me, I will call this situation here initial condition. Initial is before the lecturer here pull the string. Okay, so before he pulls the string, the mass is further away from the axis of rotation. This center here is the axis of rotation, and as you can see here, the distance of all these plastics are far away from the axis of rotation, so I give it a big R. Okay, so if I play the video, now I silence it, I play the video, you may see that it's turning at nothing so special speed, so not really fast, not really slow, a regular speed. So if that's the case, let me just write it as an omega. Okay, so we continue the video. So it's just a speed. Okay, but what happened is when the lecturer pulled the string, the Hoberman sphere contract. Okay, let's go back to that moment. When it pulls the string, the Hoberman sphere contract. And when it contract, the distance from the axis of rotation is smaller. Okay, the distance becomes smaller when it contracts. So all the plastics are now near the axis of rotation. So if it's near the axis of rotation, you can see it spins much faster than just now. So I give it a bigger omega sign. Okay, the size of the symbol that I write represents the magnitude of it. Okay, so the R here, the R here, it's big because the distance is big. The R up here is small because the distance is small. Okay, so we call that the final condition. Okay, so if our R is big over here, if our R is big, it means by our moment of inertia is big as well. If our R is small, which is the final situation, our moment of inertia will be small. Okay, so as you can see, this is a practical application of principle of conservation of angular momentum, because if I say the sum of the angular momentum initial should be equal to the sum of the angular momentum final, there's only one object, that's why I can remove the sum. Let's call it initial angular momentum equals to the final angular momentum. So in this case, there's this object initial, final. Okay, because initially the distance is big, therefore the moment of inertia initially is big. then it's rotating at a regular angular speed. Okay, nothing really special. But when I contract the Hoberman sphere, the moment of inertia gets smaller because the distance gets smaller. So if the moment of inertia gets smaller, naturally the angular velocity will become larger because both sides have to be equal. That's why this Hoberman sphere spins faster when it contracts compared to when it expands. Okay, so that's the practical application of principle of conservation of angular momentum in this particular situation. Let's look at the next one. Okay, the next one, the main actor is, yes, if you can see it, that's me. This was last year when I last year means by 2019, when I visited Pusat Sains Negara with a bunch of my classmates to discover some physics demonstration. So this is one of the demonstration. I personally demo the experiment, so let's take a look at it. Okay, so I spin. Let's see what happens with my leg. I stretch my leg, I take back my legs, I stretch out my legs, I keep back my legs. Then you can see the speed of it rotating change. Okay, it's not a very clear attempt, not as clear as the previous video, but just that because there's me, so I want to discuss about it. Okay, so let's play the video again. Oops. So that's me. Okay, so when I start spinning for first round, you can see that I stretch my leg out. If I stretch my leg out, then you can see that for this situation, I have the mass of my leg is far from the axis of rotation. The axis of rotation is around the middle, somewhere here. Okay, the mass of my leg is far from the axis of rotation. Okay, I have a big R. Therefore, I have a big moment of inertia for this case. Okay, I call it case 1 because I repeatedly take out and stretch back, take out and stretch back. I cannot really call it initial final. So this is case 1. Let's continue. So it spins at, okay, now this is another place where I keep back my legs. Now as you can see, the mass of the legs are more concentrated towards the axis of rotation. So my moment of inertia is supposed to be a bit smaller. Okay, this is the I for situation 2. Okay, it's not a subscript or superscript, I'm just labeling it's for what situation. And since the R, this one R should be much smaller. Okay, just to make it clear, it's much smaller. Okay, so this is situation 1 and situation 2. So let's replay the video again and see what's the angular speed of it moving. Okay, slow, fast, slow, fast, slow, slow. Stop. Then I get dizzy and fall. Okay, so when I stretch out my leg, it's slow, so the omega is small. When I keep back my legs, I spin faster, so the omega is bigger. Okay, this is again situation 2, this is situation 1. So if I write my principle of conservation of angular momentum, it will be L initial equals to L final. There's only one person, so no need to have sum. So I initial, omega initial equals to I final, omega final. So initially, in situation 1, okay, let's say situation 1 is initial to make it easy. Situation 1, I have a big moment of inertia. So my omega is regular. If I shrink my size, then my moment of inertia will decrease. So therefore, my angular velocity will increase. Okay. The important thing is this side and this side should be equal. Okay, that's the important thing. Okay, so that's a demonstration of me trying to demonstrate principle of conservation of angular momentum. There's a lot more application. Ice skating, the classic one. And if you happen to see a chair that can spin, you can take 2 bottles, go spin on the chair, then keep your hands towards the center. By bringing your hands towards the center, you are reducing your moment of inertia, then you spin faster. There's many things you can try. In fact, go try it out by yourself. Try to feel it. Try to experience principle of conservation of angular momentum. By experiencing it, you will remember the theory better and the theory will become more meaningful. Okay, so I'll just stop here. Thank you very much.